Paul, it looks like you're muted.
Hey, Paul, can you hear us?
Better? Can you hear me?
Yeah, that's better. Thanks.
I don't know why it's defaulting to mute. What was that, Ryan? Oh, yes. Morning. So I just summarized case one. Let's go back. Case one is when you have a zero in the first column and a zero only in the first column. That's the key thing. So a common mistake students make is they actually replace the E when they see that there's a zero there and they continue their work. So go about calculating any other coefficients in that same row and then check to see if the zero is in the first one. If it is, use case one. If not, we have to use case two, which means we have an entire row of zeros. And an entire row of zeros typically gives us a very important piece of information about our system. And what does that tell you? It'll actually help tell us if we have a marginally stable system. And we'll see that here in a little bit. So if you end up with a row of zeros, a row of zeros should always end up in an odd row. What I mean by that, it's an S to the 1, S cubed, S to the 5th, and on and on and on and on. The row immediately above that, S squared, S fourth, S to the 6th, is where we're going to pull our coefficients to build something called the auxiliary polynomial. Okay? And the auxiliary polynomial is where we'll actually get complex roots. But how do we actually use that? Well, if we have a row of zeros, we go to our auxiliary polynomial. Then we pull from our auxiliary polynomial the coefficients, and then we stuff that in and actually build an AS squared plus B, or an AS to the 4th plus BS squared plus C, on and on and on. And then we differentiate that auxiliary polynomial, and then we replace the coefficients. So if we have a row of zeros in S to the 1, we get our coefficients from S squared. And then what we do is we build our auxiliary polynomial, A of S. That's going to be equal to AS squared plus B. What should that be equal to? Is it B times S? Is that B times S? It'd be S to the 0, right? Because remember, each of these terms you skip. When you were building your Routh-Hurwitz table, your first two rows, you grab your first coefficient, then you skipped a coefficient, you grab that coefficient, you skipped until you were all the way to the end. So be very careful. Make sure that these are alternating and that you're skipping a term. Another very common mistake students will do is they'll put a 1 there. Okay, I'm just trying to give you little tips about how to avoid some of the pitfalls I've seen in the past in terms of what people will have done. So when you differentiate that, and you differentiate it with respect to S, you're going to end up with 2A times S plus B, and that's it. These coefficients here are going to replace the zeros in that. And then you can continue on your Routh-Hurwitz. Okay? So you have 3 possible outcomes from an entire row of zeros. You could have symmetric and purely real. I've never seen this, so I don't worry about that. meaning you have one on the real axis and one on the right-hand half plane and one on the left-hand half plane. Never seen it? You can have purely imaginary axis. I've seen this a lot. This is the only one I've ever seen. And lastly, you can have symmetric and real plus imaginary over here. Again, I've never seen anything like that. That would mean that you'd have to have a row of zeros in the S cubed row, right? To have 4 roots. So the one in the middle is the most common. So we'll put an X through that. All right, so here's an example. Here's our characteristic equation. S to the 4th plus S cubed plus 3S squared plus 2S plus 2. We want to go ahead and do Ruth Hurwitz. Everybody see how I got those coefficients? Everybody see where I got S to the 4th? There's a 1 here. So I grab my 1, I skip over to my 3 and skip over to my 2. Now I'm going to grab my S cubed coefficient or S cubed row. I grab my 1 from here. I grab the 2. And if you need to fill out your row, you can always go 0 S to the minus 1 if necessary, but oftentimes you don't need it. Sometimes you do if you're going to do your equations. So sometimes it's good just to put a 0 in there, just so that you show that all the terms are good to go. Okay, B1. What is B1 equal to? I had a student ask me about this a little bit yesterday. So here's the kind of the algorithm, if you will, that you're going to use. You always take the first 2 columns in the rows just preceding the coefficient you're calculating. So it always has to be the 2 rows above, and it's always the first 2 coefficients. To find the other 2 coefficients, it's always immediately to the right of the term, the B term you're trying to solve for, the C term, whatever. Okay? So to solve for B1, that's essentially my determinant that I'm doing. To solve for B2, and I'll differentiate, let's see if I can change the color. Yeah, that might be too close. To solve for B2, I'll circle B2 in blue. I'm going to use that same first column, right? That doesn't change. But now I have to grab the column that's just to the right of the term that I'm calculating. So that is where I get my second coefficients, my second terms. Okay. So here's B1. 1, 3, 1, 2, -1. And don't forget, you always pull, this number goes there. So if you're ever confused, you just pull the lower left-hand number and you pull that out because that's what you're dividing. So -1 times 2 minus 3, because it's this multiplication minus this multiplication. So that's 2 minus 3 is the determinant. Then you multiply that by -1, because -1 over 1 is just -1, and you end up with 1. Let's do B2. Everybody see now? Does that help highlight where we got the terms for B2? So again, just follow the algorithm. So to solve for B, step 1, use first column in 2 rows above for the left elements. Step 2, use column to right. I'll put immediate right. For the term you are calculating. Then you go from there. Yes, sir. -1, that's just the algorithm. It's always -1 divided by a number. It's -1. The number is the one. So for the divide by. I don't know why this isn't working anymore. It's like Microsoft messes with stuff. It's really frustrating. So divide by number is, what do we want to call that? Lower left? That's it. You have all the numbers now. Now you just have to do the determinant and you're good to go. So there's B1, B2. Plug those in. Now I'm going to calculate C1. I see there's a 0. And now all of you, almost all of you, I shouldn't say all of you, almost all of you are going to immediately substitute an E in there. Do not do that. Let's check C2 first. Why didn't I calculate C2? Is that a mistake? Is there a row of zeros here? Because right now this would tell you, hey, wait a minute, there's only a 0 in the first column, right? But in actuality, I could have calculated C2. C2 is -1, and I don't know what the divide by yet is. So it's always the first row or first column, 1, 1. And then what do I use for my other part of my determinant? 2, 2? 0, 0. So 1 times 0 is 0 minus 1 times 0 is 0. So if I'm down on this row, this S1, and it ends up being a 0, and actually all the time, this always has to be equal to 0. So you don't have to calculate this. You just know, you can see each time we go down a row, you can see that I have a 0 here, and then I've got the replacement over here where I have no term. So this would be a 0, and then that gets copied down into that step, okay? So you're just kind of moving the term and moving it closer and closer towards a 0. And the only way you do that is every other row, you should be moving diagonally down. So you can see the 2 goes here, and then it goes eventually over there. So now I can build my auxiliary polynomial, because how can I solve for D1? I know when I try to solve for D1, I'm going to get another 0, and I'm also going to divide by a 0 as well, right? So I can't even start calculating D1. So I got to build my auxiliary equation. My auxiliary equation, I got a row of zeros. Here is where I pull the coefficients for A of S. I have a 1 and a 2. So my auxiliary equation or auxiliary polynomial is S squared plus 2. Take the first derivative of that, and all I have is 2s, right? Now, this coefficient here ends up replacing the s to the 1 term. Why? Because you see that this is an s to the 1 term there. So I replace my s to the 1 coefficient, that's a 0, with the term 2. There's my 2. Now I can calculate D1. And what should D1 be equal to? Remember how I said when we presented this stuff, how do we check our work? The last coefficient. So -1/2 times 1022 equals 2. How many sign changes in the first column? None. So is this a stable system or not? 2 yeses. Do we have a quorum? Ryan? How about in TV land? Do we have a quorum? Does this indicate a stable system? One no.
Well, I guess that's not one of the sheets that were out from the question piece too. But in consistency, like
Well, remember the Ruth Hurwitz, okay? The Ruth Hurwitz, by definition, what does the Ruth Hurwitz do for us?
when did it change? The whole, right?
So every sign change indicates a pole in the right-hand half plane. Does that mean it's a stable system?
I mean, also, since we've got zero change, it kind of treat the whole thing.
Why? Are there any sign changes? What did Garrett just say?
Could have one J Omega. Look in the right hand half plane.
Yeah, the rule is it tells me how many poles in the right-hand half plane. It doesn't tell me that all poles are in the left-hand half plane. It just says here that none are in the right-hand half plane.
Oh.
So it indicates that it's not an unstable system, but it doesn't guarantee it's a stable system because it could be a marginally stable system. So led you down the wrong path. So no sign changes, no poles in the right-hand half plane. But there are a row of zeros, which means it's not going to be Bible stable. Bounded input, bounded output. And there's an auxiliary pole here. So let's go ahead and plug this into MATLAB. Remember roots? Oh, and I have 11322. Does that validate our work? I have negative numbers for all the real parts. But -0 means there's no real part for the first two. So if I wanted to do a pole zero map, everybody remember how to do that? I have to do a transfer function. So sys, what's that? That's okay. You can do numerator denominator, but I'm lazy. I like to do it all in one step. So I'm going to do my transfer function. I'm just going to have a 1 in the numerator. I think it'll work without, let me just put a bracket just in case. And then comma, then I've got to have the denominator. So I have 1, 1, 3, 2, 2. That look okay? I'm just having a random 0. So I PZ map it. Now you're all starting to see why I like to use MATLAB. You just have to have the control systems toolbox. You don't need any additional software. You just need the additional toolbox. Yeah, it's free if you are a student here. And the way to download it, so if you go to MATLAB and if you go to add-ons, you can manage your add-ons or get add-ons. So when you bring it up, if it comes on, you should see what MATLAB version you have and what toolboxes are installed. So you see here, I have the control systems toolbox. That's the one that you need. Okay. Otherwise, you can't do the transfer function stuff. It won't work. But again, all that stuff is free for you. You know, it's included with the MATLAB subscription that we have. So if you can't get this stuff, and again, I'm not expecting you or requiring you to do this. It just is another, you know, I think it's just a nice check tool, right? Because you can say, hey, Paul, you're not telling us the truth. This can't be right. I know you would check me, but now I've beaten Barzilli because he won't check me because it's like, yep, I see it here. And I can't, you know, it's hard to argue with that. Although we did get something the other day, it was close, right? It was a little bit, the number was a little bit different. Yeah. So you can see here, I've got 2 over at -5. and 2 at 0. This is a marginally stable system. Now, let me ask you a question. Could I have gotten the complex roots from some other sneaky way? It's easy way with our brains, not with math. How can I determine what those complex poles are, just purely complex, without actually having to use MATLAB? There's an equation that's screaming at you that tells you. P.S. Tell me more.
Grouping, right? You do groupings.
Ryan's on the right track. Tell me more, Ryan.
Yeah. Right.
What are the roots of this equation? Isn't that the same here? Hard to tell from the pole 0 map, but if we go all the way back to MATLAB, look right here. Oh, I can't do it. I have to annotate. Plus or minus j squared of 2, isn't it?
So that is from the where that's where it has to.
Yeah, that's from the auxiliary equation. So that's your answer. Pretty cool. Pretty helpful.
It means every time we do the auxiliary equation, it means that we have
Marginally stable. Well, not exactly, because if you remember, you do have 3 cases here. But like I said, the only one I've ever seen is this one. If you have these 2, right, it would indicate you've got a sign change. You would have a sign change. So this would basically say, okay, that would take care of that case. Same thing over here. You'd have a sign change, and you'd also have an auxiliary polynomial way out over there. So the only one I've ever seen is the middle one, which is you can use auxiliary polynomial to tell me if the roots are, or what the actual complex roots are. Yes, sir. So the question is, why did I put it in MATLAB with a 1 over here? Because my transfer function has to have a numerator and a denominator. If I have a new numerator, it's 0, right? What is something times 0 going to be equal to? It's always going to be 0. So if I have a transfer function that has a 0 in the numerator, no matter what input I provide, the output is always going to be 0. So I'd get no results. So I just put a 1 if I don't know what the numerator is going to be, just so that I can look at what the denominator poles are going to be. Doesn't mean anything other than just allows MATLAB to display it. I only do this just to show you, like, hey, this checks out the work that we have. Okay. Questions on this? So we did the check. We got this. And this one also shows you can round your roots a little bit. So this is another thing in MATLAB. I don't expect you to do the rounding, but you can certainly do something like this if you want. Here's the pole 0 map. You can see marginally stable system. Now, oh, these slides are available to you, right?
I don't know.
I mean, you're welcome to take a picture, but these slides are on Brightspace, aren't they? These are on MATLAB. These are on Brightspace. I mean, you're welcome to take photos, but you have better quality and more readily available, at least relative to the class. So. Okay, so how do you design? Remember, the whole purpose for Ruth Hurwitz is to design, because if we just wanted to do determining if it's stable or not, we could just plug this in MATLAB and we would never discuss Ruth Hurwitz. Well, now we have a variable K in there. And K is something that you all get to pick to meet certain design criteria. And one of those design criteria is how long does this rod length, this lever length need to be? How fast does the tank, can the tank fill up? You know, what is the multiplication, if you will, of the physical gain of the system, so that if you send in a small 4 to 20 milliamp control signal, what is the output that you would get? By the way, and there's somebody in the class who's going to be working in the process control industry. If you do control systems, like legit control systems from a process control perspective, anybody know what the systems work on? How do you communicate to end devices? Some stuff now is switching over to all fiber optics, so they'll use just digital communication. But a lot of people are still relying on the tried and true. They use 4 to 20 milliamps. So 4 would indicate no output. 20 milliamps would indicate 100% output. Why use 4 to 20 milliamp?
Because between 0 and 4.
It can fluctuate.
But between 0 and 4, it will be 0. So even when you press a button, so when you press it, you say all the people from all press or voltage.
But you're not, the thing about pressing a button is these are all run through controllers. So you'll actually have a controller sitting here, and then that's outputting the 4 to 20 milliamps. Yes, sir. Say more.
You always see a signal.
Yeah, exactly right. I have to have a wire, right, that goes back and forth. What if that wire is broken and it was 0 to 20 milliamps? You wouldn't know. It would be sitting there saying, hey, I'm not commanding any output, so it's 0 milliamps. So no problem. Let's run all day. So the reason why they run 4 is you at least know the wire is not broken. And there actually is detected on these controllers called broken wire detection to say that's what's happening. If you took Jude's PLC class and she covered analog stuff, that's one of the things that you actually look at is how do you know your signal is actually coming in? You did that? Look at that. Let's call back to Jude's class. So I didn't even know this when we're working together. That's good. So 4 to 20 milli is the most common. Why not go 4 to 20 amps?
Well,
Hmm?
lot of use.
A lot of juice? It could be. But the biggest reason why I like they use 4 to 20 milliamps is because if you run a lot of current, you just need bigger wires. So you can run like number 16, number 18 wire, small wire, because you're only running milliamps of current. And you can run that out there. And with low current levels like that, remember what current does, it creates magnetic fields. And if you have tens of thousands of wires carrying 20 amps possibly, you're getting a lot of magnetic field, and then they start to interact with each other and you can produce noise and cause issues. So long time ago, 4 to 20 milliamps is what they do. It's actually kind of a joke because the 4 to 20 milliamp, if you go to an end device, the very first thing they do is put a precision 250 ohm resistor on it to convert that milliamps to a voltage. And then you use your A to D converter to convert that voltage to that. So that's all A to D converters have is they have a built-in resistor. You just don't see it. Isaiah. Less voltage, yeah, voltage drop, yeah, exactly. Yep. So there are some advantages for sure to do 4 to 20 milliamps. But a lot of stuff, like I said now, is transitioning to fiber. You could even use wireless. But the problem with wireless is it's not, you know, the most robust. Even if you have a very reliable wireless system, you can still have people hack you. You can still introduce noise. And so if it's any process control, anything I've seen, but again, I'm going back a few years, all the stuff I've seen always wants a hardwired input signal to it. And again, it could be fiber or, you know, Ethernet or whatever. I used to use Ethernet. I think everything now is fiber just because it's easier to have a network and do it that way. But one of the problems with all this stuff is the bad guys, right? You can hack into somebody's system and now you can go ahead and you can monkey around with a lot of different things. Okay, so just a side topic, but if you look at, they're called I to Ps. So current to pneumatic would be one, an I to I, current to current transducer. Those are the ones where you'll see that they call them P and IDs, piping and instrumentation diagrams. You'll actually see all these sketches with instrument numbers and all that stuff. You'll actually see those type of things. So if you were to go over to Jeunesse, they have some P and IDs. In the utility world where we typically work, we don't see P and IDs all that much unless you're at a generating station. So if you went to Main Independent Station, they have piping and instrumentation diagrams all over the place because that's actually how they describe their mechanical systems in terms of water or air or whatever, and how you're controlling things, because we live in the real world and we have to have water doing things, right? Back in the day, when I was starting out, a lot of stuff was controlled pneumatically. So you'd have to have big air compressor systems and all that stuff that actually would push on butterfly valves. So you'd have a flapper piece of rubber that would be connected to a valve, and you just pressurize it and you move it up or down to open or close the valve. Now, a lot of those are going away because electrical solenoids can do that just as effectively. And now you don't have air leaks to worry about, right? Because it used to be you'd be running around chasing, people would spend months chasing around air leaks. So you'd hire a crew to come in and they'd go down and they would snoop. Anybody know what the snoop stuff is? Soapy water. Every joint they'd come across, you'd spray soapy water on it, and you could see if it bubbles. If it bubbles, you'd try to tighten down some fittings. If not, you'd have to redo them. So people would spend millions of dollars just looking for air leaks, because these lines are only, I think they're 3/8 of an inch diameter lines, really small, because you just need compressed air, whatever volume you need. So interesting stuff, I thought. All right, so determine the range of K, what it needs to be for which the system is going to be stable. And I know that K has got to be greater than 0 because you can't have a lever length that's a negative lever length. That wouldn't exist. So we're going to pick our value of K. So the first thing we have to do is solve for the characteristic equation of this particular block. So G of S over 1 plus GH gives me my transfer function here. Now I'm going to go ahead and build my roof. So I take these and these to get my table. Now I solve for B1. 1,386 minus K divided by 18 is the first one. Solve for C1. Why did I solve for B1? Or I'm sorry, B2. Didn't solve for B2 because I know it's going to be 0, right? Because if I was to use and fill those terms, I know that the column just to the right of that is going to be filled with 0. So there's no reason to calculate it, but you're welcome to check with B2 to see if you have. Now here's my value of K. Now I need to make sure that the system is stable. So this is a plus. This is a plus. What does the result of this need to be? Plus. What about here? So I know the only thing that makes this number in the row S1 go negative is if the numerator is negative. And I know over here, the only way this goes negative is if K is less than 0. So this one requires us to be K greater than 0. This one, 1,386 divided by K, has to be greater than 0. So you can multiply both sides of the denominator. And remember, this is where it gets tricky, right? So what we did the other day was, we just moved K to the other side. Correct? And that works out okay. K has to be less than 1386. The other thing you can do, which I usually never move my K, just as a practice for me, I never move my K on either side of the equality. The way that I typically do this is I would say negative K has to be greater than negative 1386. And then I'm going to multiply both sides by -1. And when I do that, I have to flip-flop the sign, the equality. Okay, this is just the way that I do it. I never move my K. Because you can make mistakes about your equality. So K has to be between 0 and 1386. Yes, sir. Where'd the 18 go? Multiply both sides by 18. What happens to the right-hand side? 0 times 18 is 0. So you really can just focus on the numerator. Don't even have to focus on the denominator. All right, 5 minutes, party people. Your turn. I have 8:35. I'll check in at 8:40. What's that? Oh. Couple more minutes. For those of you having a hard time getting started, I'll give you the layout. Get you started right. No, they're doing an in-class activity.
Oh. Maybe the two views where they go with all flex and then you will have to figure out everything.
All right, what'd you get? What's the value of K?
What's that?
I'll work independently.
What you did, all right.
Okay. That's what I had for my term. Okay. And then I'm going to go ahead and continue. But I know that this last term, I don't even need to check it. This is 4. This is B1. So for this to have all poles in the left-hand half plane, not a stable system, but all poles in the left-hand half plane, I can't have any negative numbers. Positive, 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 positive. So the first one is 3K has to be greater than or equal to 0, which means K has to be greater than or equal to 0. That's an easy one. The next one is 3K squared minus 6K minus 4 all over 3K has to be greater than 0, right? So this right here, this K being greater than or equal to 0, we also have to be careful because this can be infinity, but that's okay. We can cross that out. So 3K squared minus 6K minus 4 has to be greater than or equal to 0. What do we do now? You have two feelings?
The first one we can do the quadratic, right?
The what?
Quadratic,
Yeah, why not just use a quadratic equation?
but also we could send it to -4, but that's fine. And fuck K. But that's what I want you to see because.
Send the -4 to the other side and factor K.
Yeah. It might be legal.
I don't think that it's illegal. It's just that why would you do all this extra algebra? If you have it in a form right here, you can just do quadratic equation.
Because if you fuck at K, then have K bracket 3K minus 6 greater or equal to 4.
Well, let's check it. Let's see if we get the same result. So your approach that you're suggesting is if you factor out K, 3K,
Yeah.
sorry, K, no, 3K.
Yeah. Greater than 4.
So that would imply that K has to be greater than 4 or the other one. So this implies K is going to be greater than or equal to 4.
K would be greater than.
No. Well, you can't say K is going to be greater than or equal to 4. You'd have to say K is going to be greater than or equal to 4 over 3K minus 6, right? Because I brought a 4 over here, it's not a 0.
Oh, yeah.
So that doesn't really help me all that much because I still have, it's an inequality. So I've got to solve for K, right?
What have a K greater than 4 or K greater than 6 or 4.
If I can't say K is greater than 4 because if I plug in 4 in here, this is 12 minus 6, right? So that would be, I mean, it would meet that rule, but we're just looking for it being positive number. So let's do the quadratic equation. Negative B plus or minus square root of B squared. Oh, negative B, no. B squared 36 minus 16, which is equal to 20. Wait a minute, not 20. It's positive. I'm so used to having negative numbers there or positive numbers there. So it's negative B. So 6 plus or minus the square root of b squared. So 6 times negative 6, that's still 36. Minus 4 times a times c. So 4 times -4 is -16. Times 12 is, or 3 is, what's that? 48. All over 2a. So what does this tell you? We're dead in the water because it's 36 minus 48. That's a complex number.
Paul, that'd be plus 48 because you're multiplying by
Oh
the
yeah,
negative
plus
as
48.
well.
Oh,
We're good.
Geez, I'm all over the place. So it's 6 plus or minus 36 plus 48, which is 84 over 12. What's the square root of 84? 9 and change. It's all over 2a, so it's 6, not. I'm obviously off my math game. So this is 6. This is right, because it's 2 times a, which is 2 times 3. So 84 is 9 and change. So we know that we can't subtract negative. Why not? Because k has to be equal to 0. So the only thing that it can be is k has to be greater than 0 for here, but also k has to be greater than 6 plus the square root of 84 all over 6. So this is the limiting one to make sure that that's that value. So as long as k is greater than that, which is going to be greater than 4, right? So that's why this technique here doesn't work for us because of the inequality. And that's it for characteristic equation in Ruth Hurwitz. This is like one of the funnest sections for me to teach because it like just kind of lays out a lot of stuff. And it really does a pretty good job of, you know, it's kind of like gives you a really powerful tool without doing a tremendous amount of work. And it's not a really difficult concept to grasp. And it gives you an easy, like, what is my value of k? Because once we start doing root locus and Bode plots, that's a lot more concept stuff where you're doing plots. This is like you get the number and here's what it is. There's a couple of equations, but they're not super complicated. He's mocking me. Let's check over here. Let's check this value right here real quick. You see with this value of k? What happens if k is equal to 1386? So a fair game question, I think. A fair game question is find me the value of k that results in a marginally stable system. So if you remember my S1 row, it was 1386 minus k over 18 and 0. So if k equals 1386, that becomes a 0, right? So if I look over here, 18 plus k is my auxiliary equation. So 18 s squared plus 1386 is going to have to be equal to 0. If I solve, s is going to be equal to negative 1386 over 18 square rooted. And that's what we would get for complex conjugate pairs, right? We get those with our complex roots. Let's check that. So here is our characteristic equation right here, or I mean our transfer function. So let's build that in MATLAB. So my system is going to be equal to transfer function In the numerator, I have 1386. And in the denominator, I have, let's,
Give you zero.
well, that's okay, let's try it, because I want a marginally stable system, so I have 1, 18. I think MATLAB can do this. 77, and the value of K. Yeah, that's my transfer function. Now let's pull PZ map that one. And here we go. At K equals 1386 becomes right at marginally stable. So a thing could be is find me the value of K that makes this an oscillator. So sometimes you use this auxiliary equation or the zeros to get a row of zeros so that you can pick a value of K so that you know that you get a marginally stable system. And remember what we did? We did this by hand, right? Where we said we said, where's it? That was right here. So I said 1386. I said we solve for that right there, 1386. So if I do the square root of divided by 18, 8.775. How did I do? MATLAB says 8.77, right? I had 8.775, so we're pretty close. So we can check MATLAB and see if they're wrong.
We can always do the auxiliary equation.
The only time you will have an auxiliary equation if you have a row of zeros.
Oh, I see.
I forced this to be a row of zeros by making K equal to 1386. But like I said, I like teaching this stuff, but I just think this is like one of the most concrete topics you'll talk about from a control systems perspective. And remember, I sort of lied to you last semester. I said, remember when you're in the Laplace domain? What did I say you won't have to do? I didn't say math. I said you won't have to do calculus, but we did have to do a derivative to get our auxiliary equation, right? But I didn't say you'd never have to do calculus. I just said we'd do it as little as possible. And this is one of those instances where we actually have to do derivatives. Okay, not a hard derivative though, fortunately.
But come with that.
Questions? Good stuff, bad stuff, in between stuff? Yeah, because I'll post the next homework after class. And it'll probably be due, do you want it to be due the Tuesday you get back from break or the Thursday? Okay. And then we'll probably have a test the week after that. Fair enough. Because we'll have our next test. We could have our next test the week after break. The hard part is that in my other class, I have a test the week after break.
Yeah, put that hand down.
All right. I'm not going to try to cram in new material, so I just figured I would talk a little bit about this stuff, and that's it. Any questions from TV land?
No, sounds good.
All right. Have a great day, everyone, and I'll talk to you later. Take care.